All right, so chapter 7 of the Memlers, right? So we're looking at bones and joints. So bones are obviously going to be like, you know, the stuff that gives our skeletal system its hard framework and protects all of our delicate structures and stuff. We'll talk a little bit about their anatomy and their physiology, and we'll briefly talk about their markings, which is kind of fun. We'll move on to the sections of the skeleton. You know, the axial skeleton, which is basically like your skull and your vertebrae and your rib cage and things like that. And then we'll look at the appendicular skeleton, arms and legs. We'll talk about very briefly certain disorders of the skeletal system. And then we'll talk a lot about joints, which is really fun because we'll look at the different types of joints and we'll talk a little bit about their disorders. And then we will talk very briefly about how aging affects the skeleton here. So some key terms to look out for, you know, here at the top of the PowerPoint and stuff. But let's go ahead and just define our skeletal system right off the bat here, right? So your skeletal system, a lot of people think it's, you know, it's just the bones, right? Like their knowledge of the skeletal system is, you know, it's like, yeah, it's the bones inside my body. But it's actually, when we talk about the system, the skeletal system, right? Remember yesterday, or not yesterday, 2 days, our first day of class, we talked about how like our levels of organization, right? We have chemicals that make up cells, cells make up tissues, tissues make up organs, and then organs come together to make up systems. So any group of tissues is going to be considered an organ, which means that technically every single one of your bones individually is its own organ, right? And so like where this bone attaches to another bone, you know, we got to have something that like holds them in place. So at your knee joint, for instance, like I'm just going to pull up a picture of the knee joint so you guys know what I'm yeah, the snowboarding stuff. You know, if we look at the structures inside of our knee joint here, you'll see all of these like specialized little material. Actually, I do like that one. You can see like there's some ligaments there that are holding the bones together. There's your meniscus here and your meniscus here. And there's cartilage running throughout the whole thing. So that's all part of the skeletal system as well, right? And so, you know, this little ligament is technically its own little organ, and it works together with the other ligaments in the knee to hold everything together. And so like that's kind of a big part of when we're looking at these structures here. So your skeletal system is not just your bones. It's your bones, the joint itself, which is this cavity here, and the connective tissue that holds all of it together, right? So it's your bones, joints, and connective tissue. And I forgot how much I love this picture. It's like we got Captain Morgan as like a skeleton here. But here's what we're talking about when we look at the skeleton, right? And you can see they've highlighted it into 2 different colors here. You can see the skull, vertebra, and then rib cage. That's all sort of in this color. And then we see like the arms and legs with the pelvis and the collarbone and the scapula holding those on. These are the 2 main divisions of our skeletal system, right? Like this is your axial skeleton here. It's what protects all of your vital organs, including your brain, and then like, you know, provides an anchor point for your appendicular skeleton to attach to. So you've got your shoulder blade, your scapula, which you can't really, it's kind of hard to see in this picture because it's behind everything, but you get your shoulder blade behind, and then it attaches with your collarbone here. And this is what's kind of fun here. The scapula is not actually attached with any ligaments in the upper back. So there's nothing actually holding the back of your shoulder blade onto your whole body. In fact, the only thing that's holding your entire arm on is this little tiny joint right here where your sternum is meeting with your clavicle. It's called your SC joint or your sternoclavicular joint. And that's the only thing that holds your entire arm on, this little tiny pin right here at your collarbone. That keeps your, you know, the thing that you do pull-ups on, right? Like this little itty bitty tiny joint right there. And then that runs across your collarbone, and it's got another joint right over here. I shouldn't say it's the only thing, but it's the only like bone on bone connection that your arms have to your axial skeleton. There's obviously a lot of muscle in the upper back that's holding that together, but that's what we call a false joint actually, because it's not like it's not a real joint. It's just false in the sense that it doesn't have any ligaments or anything. And then your pelvis, kind of similar, actually. You can see there's your sacrum right there, and then there's the coccyx down below it. That's your actual tailbone. But you can see like the sacrum, this little triangle-shaped bone, is holding together both sides of the pelvis here. And so like now you can see the skull traveling down and then ends in the sacrum there, and then that attaches to, these really, really big sides of your pelvis that we call your acetabulum, right? This entire pelvic structure here, and then that holds both of your legs on. So that is the two main divisions of our skeletal, right? And so we look at like what our skeletal system does, right? Again, it's made up of bones, joints, and connective tissue. So your bones are going to act as the framework of your body, right? This very hard tissue that gives us like form and function. Like if we didn't have a skeletal system, we would just be this kind of like, gooey mess on the floor that would like be able to quiver a little bit and not really like move around very effectively, right? We'd have to basically move around the same way that like, amoebas and starfishes and leeches and stuff. These are kind of like weird little animals that don't have much like skeletal system to them. So that's a really good one. It's going to protect all of our delicate structures. It's also going to store calcium in our body. I mean, your skeletal system is primarily made up of calcium, but it's great because like that means that we've got calcium stored in our body anytime we happen to need it. And one of the things we're going to look at when we look at the muscular system is that we need calcium in order to create muscular contraction. So that's actually a really big one. It also produces your blood cells, both your white and your red blood cells. You get your white cells being created in your yellow marrow, and you've got your red blood cells being created in your red marrow. And that's really, really important because that, gives us an immune system, allows us to deliver oxygen throughout the body. And then, and this one's in italics here because it's the most important for our conversation, even though it's not necessarily in the PowerPoint here. The most important thing that your skeletal system does, that all your bones do, they act as levers for your muscular system to manipulate. So they actually are acting as like the things that your skeletal system moves around, right? So like I'll have a muscle that will run over top of the shoulder and attach down here. And when it pulls like this, that raises my arm up to the side, right? And so when I pull and I do this kind of action, that creates like a lever, and then that lever can be manipulated by my muscular system. And then that whole muscular system is controlled by my nervous system. So, these are the three main areas that we're going to talk about over the next couple of days: your muscular, skeletal, and nervous systems. So looking at your bone structure, you can see we've got the ends here. These are called your epiphyses. They're the knobby bits on the end of all your bones. Then you've got your diaphysis at the, which is in the center here. This is where you're going to find the different types of bone marrows that you've got, right? So you can see like all this big spongy bone here. They call it spongy bone because like it kind of looks like a sponge. It's actually a little softer than normal. That is going to contain all of your red marrow. And then you're going to have some yellow marrow here in like the middle of the bone, right? That in the diaphyses there. And then when you look at it, and you can kind of see it here, they're drawing it very, very simply. You can see it's got this outer like layer, this outer wrapping around the outside of all of your bones. That's called your periosteum. And that outer wrapping is a form of fascia, which if you've been through some of our other classes, we've mentioned fascia before, but fascia is basically the wrapping around all of your body, right? Like technically your outermost layer of skin is like fascia, right? But the more common version that we talk about is like the fascia that covers around your muscles. If you've ever been cutting like a piece of chicken or like steak, and you can find that like silver skin stuff that you got to kind of cut through, and it's like real stretchy, and it's like a wrapper around the meat, right? That silver skin is the fascia of that muscle. Well, there's fascia covering everything. There's this outer layer of fascia that's got to protect those structures and keep them in place. And so there's a little bit of this on the outside of our bones. And you may be familiar with this outer layer if you've ever had shin splints. I don't know if anybody in here has ever had shin splints from like running, maybe through like high impact and stuff. But it feels like somebody took oh, Cody, you had some shin splints?
Yeah, they freaking sucked.
Mm-hmm.
I got one during a football practice.
I believe it, man. It hurts, right? It's painful.
Oh
Um,
yeah, I couldn't run or do anything for at least a couple weeks.
yeah, it feels like somebody took like a, not like a hammer, but like a rubber mallet and just smacked your shins all day, you know? Um, yeah, so that's actually an example of where you basically get a lot of fractures and inflammation on this outermost layer in your shin bones, you know? We call that um, posterior tibialis syndrome. So looking at this, right, when we look at like your bone tissue, you can see your bones are actually kind of this hollow honeycomb network. When you look at them, you'll see, you know, they arrange themselves in these kind of interesting little rings, right? Kind of looks like the rings of like a tree, you know, like, you know, you saw through it and you can count how old the tree is. You can't do that with your bones, so, you know, but you can see they do form these like little rings here. And what that does is, you know, they kind of alternate in different directions. So do I have a good picture of that? I don't have a good picture of that. So they actually alternate themselves. So, you know, this ring might twist slightly at an angle like this, and the other ring might twist slightly at an angle like that. And so it creates this like cross section in two different directions. And that allows your bones to have this really great structure that can resist like a little bit of like flexion, right? Like if you were to take like a bone and just bend it ever so slightly, it would be pretty good at like resisting that while still maintaining like a very hard structure. And then there is also all of these blood vessels that are running through it. That's how, after your red blood cells or white blood cells get made, that's how they can enter the rest of the body. And then there's also like blood there that's being delivered to the bones to, you know, keep them alive. Um, so that is sort of what we look at when we're looking at like our bone tissue. Now, the really important thing that we need to talk about, or one of the most important things we need to talk about, is one of the things that we try to trigger in our clients is helping them maintain or generate greater levels of bone density, right? So we are trying to like have our clients have the densest bone possible. The denser your bone is, the less likely it is to fracture under certain types of stresses, right? So, you know, your body is you're constantly damaging your bones. Like normally, in fact, in class, one of my favorite things to do is to go up and give somebody like a really hard high five. And I go, now, I just fractured some of the bones in that person's hands, right? Like just really tiny little micro fractures. It's not gonna hurt too bad, but like that little bit of impact, right? Or if you think about like jumping or, you know, lifting really, really heavy weights, imagine you're doing like a barbell squat, right? Imagine you've got like a really heavy barbell on your back and you're squatting down, right? Your bones are just, they're bending a little bit under that really heavy weight because you got this muscle that's grabbing one side of that bone and pulling really, 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 really hard. So because of that, you might you know, you're causing this bending action, which could cause the bone to fracture ever so slightly, right? So when we look at that, when we look at like this fracturing action that happens, right? That needs to be repaired. And they're microfractures. These are the good types of fractures. You know, when I say fractures, I don't mean like, you know, the type that we're kind of thinking of when we think of like breaking through a bone or something. We're talking about like little tiny itty bitty microfractures, which are the good kind, right? Think about it this way. If you've ever taken like a number 2 pencil or like a stick, right? And you bend it and you eventually start to hear that like right before it actually like snaps. Those little tiny like those little itty bitty breaks are little micro fractures, right? And if you stop, you know, the pencil's gonna be fine. You know, you're not gonna break all the way through it, but you did damage some of the fibers on the inside of it. That's happening to your bones constantly. So we have to have a way that we can delete all the damaged bone tissue, you know, and lay down new bone tissue. But here's the thing, and this is the first time we're going to talk about this in this class. Your body's really good about not just repairing stuff back to neutral. Your body is actually really good at repairing stuff and making it more resistant to damage next time. And here's what's really fun. This is one of my favorite weird facts. We don't know why that happens. We have no idea why the body is actually programmed to build muscle, you know, or build bone tissue up stronger than it was. We know how to make it happen. You know, if you go lift heavy weights, your body will increase bone density, your body will increase muscle mass, but we really don't know why. Our DNA is kind of programmed that way, but it's a good thing that it is, right? Because basically I always like to think of it as like a repair crew inside of my body, you know? And it's like, you know, I go do like a really heavy workout, and then that repair crew comes along and they're like, what did you do? Oh, you tore everything up, right? And then like they got to fix it all. And then like I go do that same workout again a couple days later, and they're like, stop it. You keep breaking everything down, you know? And then like, they're like, all right, if you're going to keep breaking this stuff down, I'm going to keep building this stuff up. But I don't want to keep building this stuff up. So I'm going to build it up stronger and more resistant to damage. And then all of a sudden we add a couple plates, you know, onto the bar, and we lift a little bit heavier. And now we can create, you know, more damage, right? And so it's a kind of a constant war between your body's immune system repairing and you know, creating damage. That's why you don't build muscle in the gym. You break muscle in the gym. And the same thing is true of your bones. So the cells that do this, right? The cells that are responsible for repairing your bone tissue, this whole process, by the way, we're going to call this process bone resorption or bone remodeling, okay? So bone resorption is the process of breaking down old bone tissue, right? So bone resorption is where your immune system comes along and it eats away any bone tissue that is damaged, right? And then what that does is now you don't have any imperfections in your bone. You get this nice smooth area, and some more bones can come along and lay down better, stronger bone tissue, right? So this is a very important part of bone remodeling, and the cells that do that are these specialized cells called osteoclasts, okay? You can think of osteoclasts as bone breaker downers, okay? Their job is to come along and resorb old bone. Basically, they've got a whole bunch of enzymes, and they come along and they eat your bone tissue and they take away any imperfections. Now that may sound kind of like a bad thing. You're like, I don't want something eating my bones, right? But luckily osteoclasts work really well in conjunction with these other cells called your osteoblasts. And your osteoblasts are specialized cells that are responsible for building up new bone tissue, okay? And so osteoclasts will come along and destroy like a small section, leaving it open for like new construction, right? Like, and then your osteoblasts come along and they lay down, you know, all this material that basically attracts calcium, and that builds up your new, stronger bone tissue, right? Those osteoblasts are your bone builder uppers. You'll definitely want to have both of these terms straight in your head. We've got a lot of questions. You know, throughout the program that are related to these. So osteoclasts break bone tissue, osteoblasts build up new bone tissue, and that is how your body is able to form and maintain and repair your skeletal system, right? That's what happens a lot when you're younger, especially, right? When we're younger, our osteoblasts are really active. You know, they're constantly trying to build up new bone tissue. But as we get older, our osteoclasts actually become more active. And they start to break down bone tissue faster than the osteoblasts can repair it. Because basically, as you get older, your metabolism starts to slow, right? And so since you have that ever so slightly like slower metabolism, your body's trying to find a way to, like, you know, maintain balance. Your body's trying to find a way to stay in a calorie neutral zone. So if it's like, hey, we can get rid of some muscle tissue, we can get rid of some bone tissue, you know, that stuff's going to make us burn a lot less energy. And so what it'll do is it will actually like get rid of anything that you're not using. This is why it's so important to exercise as like a senior, because that's going to ensure that like you're damaging your bone tissue, and that will trigger the growth of new bone tissue, which means that your body will go, oh, okay, well, I guess I use this stuff pretty frequently. I probably shouldn't get rid of it, you know? So that's sort of bone resorption there as like in a nutshell, right? So I want to show you guys a quick little video here talking about bones. We got a crash course. We got 2 crash course videos today. Let's see, crash course skeletal system. And we want this one. All right, here we go. Yeah. He picks the most fun bone here at the beginning, by the way.
This, my friends, is a walrus baculum. It's basically a penis bone found in most placental mammals, interestingly not in humans. And this is a polar bear skull, which as you can see is more streamlined for swimming in the water than a grizzly bear skull. And over here we have my giant friend, the rhino head, which is good for being giant, for fighting off predators and fighting for, I don't know why do rhinos have big heads. And this is the skull of a pronghorn antelope. It has these horns that come off that are covered in these keratin sheaths that fall off once a year. These are all bones, parts of skeletons, and they're all pretty freaking awesome, and I'm surrounded by them here at the Philip L. Wright Zoological Museum at the University of Montana. And all of these bones have adapted to help animals survive. The horns on the pronghorn for mating displays and self-defense, the streamlined skull of a polar bear for swimming in the water, and the walrus baculum for longevity, I guess. We're used to thinking of our skeletons as being the dead parts of us because that's what's left over after all of our stuff that looks like us has rotted away. But the fact is, our bones make up a vital organ system, and I don't just mean vital in that without them you would be a sort of disgusting dead pile of lumpy mush, but also in the traditional meaning of vital, meaning it's alive. It protects your vital organs, it makes locomotion possible, it manufactures your blood, and on top of it all, it takes care of its own repair and maintenance. Your skeleton is alive, people, and walrus penises are just the beginning.
All right, muting that for just a second and then bring it back up.
So you know what bones are, but maybe you didn't know that you don't have to be a vertebrate or even a chordate to have a skeleton. Jellies and worms, for instance, have hydrostatic skeletons made up of fluid-filled body cavities. By squeezing muscles around the cavities, they change their shapes, and that can be used to produce movement. Insects have exoskeletons, of course, made of the nitrogenous carbohydrate chitin, and most mollusks have exoskeletons too, in the form of calcium carbonate shells. But when it comes to skeletons, the winningest formula has been the endoskeleton, even though we'd probably feel a lot safer if we were covered with armored plates like some race of Iron Men. Having skeletons inside of our bodies has allowed us to grow larger and have much more freedom of movement. Good stuff. One of the many reasons you don't see ants the size of horses walking around is, well, one, it wouldn't be able to breathe, but also a body with such a huge volume would require an exoskeleton that was exponentially thicker and therefore heavier and clumsier to support it. So endoskeletons allow animals to grow larger by supporting more mass. Plus, you don't have to worry about the embarrassment that comes with unsightly molting. As adults, humans have 206 bones, all kinds of shapes and sizes, including 3 tiny ones in each ear, 1 weird-shaped one like a horseshoe in your throat, 27 in your hands, and 26 in each foot. You also have at least 32 teeth unless you play too much hockey, and even though they're included in the skeletal system, they don't count as bones because they're made up of different material, namely dentin and enamel, the hardest material in your body. And you probably think of the skull as one big bone, but it actually consists of many separate bones, including 8 plates that cover your brain and 14 others in your face. Face bones. So simple, right? Well, you might want to sit down, you probably already are, but I'm going to, because it's time for biolography.
Also loud.
That we'd have nailed down the basics of the human skeleton a long time ago because our teeth and our bones are the biggest and hardest parts of our bodies. And after we leave this mortal coil, they're what stick around the longest. It's not like they're super hard to find and study. Surely all of those ancient physicians who basically invented medical science would have inventoried all of our bones pretty soon after they figured out that we had bones, right? If the answer was yes, do you think I'd be sitting here? Most of what we know about the human skeletal system is thanks to Andries van Vessel, who was born in what's now Belgium in 1513. And in those days, if you were like a kung fu master of science, you pretty much got your own Latin name. So today, he's known as Andreas Vesalius. Vesalius came from a long line of physicians to kings and emperors, and while studying in Paris, he began dorking around in cemeteries and became interested in what's now known as osteology, the study of bones. Perhaps Vesalius' greatest contribution was showing the world that everything we thought we knew about osteology was wrong. See, back in those days, if you wanted to become a doctor, you didn't study bodies or see patients. You read stuff written by ancient Romans whose work was considered indisputable. Because, you know, those guys had long beards and they wore robes. But in his research, Vesalius discovered that Roman texts about the skeleton, especially the teachings of the philosopher Dr. Galen, were way, way off. See, Roman law prohibited the dissection of human bodies, so none of those guys ever actually studied human innards. Instead, they dissected apes and pigs and donkeys and used that to make assumptions about the human body. And so for 15 centuries, young doctors were taught those assumptions. But Vesalius revolutionized osteology and all of medicine by introducing a new practice, every pre-med student's favorite, human dissection. He instructed students by dismembering corpses in front of them and cataloging their parts, giving students the first opportunity ever to directly observe the inside of a human body. These new methods drew a lot of attention, particularly from a local judge who began donating bodies of the criminals that he executed to Vesalius. Suddenly, the dude was up to his codpiece in pig thieves and murderers, and by the time he was 28, he'd done enough research that he published De Humani Corporis Fabrica, on the fabric of the human body, a 7-volume text on human anatomy, including the first comprehensive description ever made of the human skeleton. Its beautifully detailed illustrations are thought to have been created in the studio of the Renaissance artist Titian, featuring pictures of flayed corpses positioned in symbolic poses, and many of the volumes, some of which still exist today, are bound in human skin. So the takeaway here is that even though bones are big and hard, the science behind them is far from obvious. Even though we tend to think of our bones as rigid and fixed, your skeleton is as dynamic as any other of your organ systems. It's built from scratch with ingredients in your blood. It's grown according to glands in your head, and probably coolest of all, it's constantly breaking itself down and rebuilding itself over and over again for as long as you live. Most new bone tissue starts out as cartilage, which you may know from your nose and your ears. It's made of specialized cells called chondrites, and in newly forming bones, these cells start dividing like crazy and secrete collagen and other proteins to form a cartilage model or framework for the bones to form on. Soon, blood vessels work their way into the cartilage and bring plump little cells called osteoblasts. Oste, which you'll be hearing a lot of today, just means bone, and blast means germ or bud. The bone building that they do is called fittingly ossification. First, they secrete this gelatinous goo that's a combination of collagen and a polysaccharide that acts kind of like an organic glue. Then they start absorbing a bunch of minerals and salts from the blood and all the capillaries around them. And unsurprisingly, they're especially absorbing calcium and phosphate. And they begin depositing those minerals onto the matrix. With the help of enzymes secreted by the osteoblast, these chemicals bond to form calcium phosphate, which crystallizes to make your bone matrix. In the end, about 2/3 of your bone matrix is proteins like collagen, and the other third is calcium phosphate. Kind of surprising, right? Most of your bone isn't even mineral, and even the part that is living tissue, because it's all honeycombed with blood vessels that allow osteoblasts and other cells to do their jobs. Unlike an insect's exoskeleton, even the hardest parts of your bones are alive. Now, even though bone can take all kinds of forms, from big flat plates protecting the brain to the tiny stirrup in your ear, inside they all tend to have the same basic structure. If you cut one in half, you'd see that the matrix actually forms in 2 layers. The outer layer, called the compact or cortical bone, is hard and dense and makes up about 80% of the bone's mass. In the middle, the spongy or trabecular bone is softer and more porous and contains the marrow and fatty tissues in larger bones. The marrow, of course, makes not only new red blood cells, but almost all of your different blood cells by a process called hematopoiesis. I'd need like about a week of your time in a Greek dictionary to explain how it does this, but suffice it to say that evolution has wisely chosen the innards of our largest bones to house the blood stem cells that together can produce 1 trillion blood cells in you every day. 10 to the frickin' 12th. On the outside, the larger bones of your body have a similar structure. Have a look here at this femur. That's the biggest bone in your body. The main shaft is called the diaphysis, and each rounded end is an epiphysis. When the bones grow, as a child grows, the new tissue forms the border between the two, a place called the epiphyseal plate. As they did when they formed the original bone tissue, chondrocytes start to produce new cartilage here, and the osteoblasts come in and lay down more collagen and calcium phosphate. So as you grow, the ends of your bones are actually growing away from each other, until by the time you're about 25, the last of these plates in your bones harden. By the way, this whole process is stimulated by growth hormones secreted from glands all over your body. But the head honcho right here is the pituitary gland, about the size of a pea, nestled at the base of your brain. As adults, this and other glands produce less growth hormone, which slows down our bone lengthening. But even though lengthening is a limited time only process, the thickness and strength of a bone must continually be maintained by the body. Because, of course, like all of your cells, bone cells go through a lot of wear and tear and need to be able to adjust to changing conditions. So over the course of each year of your adult life, about 10% of your skeleton is completely broken down and then rebuilt from scratch in a process called bone remodeling. Here, the main players are the osteoblasts, again, and another kind of cell that's kind of their complete opposite, the osteoclasts, or bone breakers. You'd think maybe that the cells that form bone tissue and the ones that destroy it would be in some kind of constant battle in your body, but during remodeling, they work closely together and actually communicate nicely. It's like they're basically frenemies. Remodeling begins when osteoclasts are sent by way of hormone signals through the capillaries to the sites of microscopic fractures in the bone matrix. Once they're in place, they secrete an acidic cocktail of hydrogen ions to dissolve the calcium phosphate into calcium ions, phosphate, and water, and other material that they carry back to nearby capillaries. Then they secrete enzymes that specialize in digesting collagen. This whole process is called resorption, and when the old bone tissue has been cleaned up, the osteoclasts send out a hormone shout out to the osteoblasts, who come in and do their ossification thing. Bone remodeling is really pretty amazing, and it's all ultimately regulated by hormones that maintain the levels of calcium in your blood. The glands that call all the plays during the bone breaking part of the remodeling are the parathyroids in your neck. When the calcium in your blood plasma falls below the level of homeostasis, the parathyroid triggers osteoclasts to take calcium out of your bones and release it back into the blood. Likewise, when blood calcium levels are too high, the parathyroid's cousin, the thyroid gland, signals osteoblasts to take calcium out of the blood and lay it down on the bone collagen through more ossification. And remember last week when we talked about how the kidneys reabsorb salts and minerals? Well, the thyroid also regulates how much calcium is reabsorbed in that process, as well as the amount of vitamin D, because vitamin D helps your body absorb calcium through the small intestine. And that is why vitamin D is all good for your bones and stuff. Now, the relation of active osteoblast to active osteoclast can change dramatically under different conditions. The more you stress your bones, the more osteoclasts work to break down the bone matrix so that it can be reformed. Bone stress can include stuff like fractures, of course, but it can also be less traumatic and more sustained. Exercise causes stress on the skeleton that helps stimulate bone remodeling. So when you're working out, you're not only building muscle, you're also building bone. So as you can tell, it's kind of hard to talk about bones without also talking about muscles. And that's what we're going to do on the next episode of Crash Course Biology. Thank you so much to the Philip L. Wright Zoological Museum at the University of Montana. Sorry, I just hit you. Check out their Tumblr at umzoology.tumblr.com. It's awesome. If you want to review anything, table of contents, just click on it or just rewatch the whole episode because you know you liked it. And if you have any questions for us, of course, we will be in the comments below, as will all of the super helpful people who are always answering questions who are not us. Thank you to those people, by the way. And we will see you next time on Crash Course Biology.
Okay. So yeah, it is. It's a constant, it's this constant thing that's kind of happening inside of our body. We're building up new bone tissue, but we have to first break down old bone tissue. One of the things that he doesn't mention too much in detail there is where he's talking about the idea of when your osteoclasts break stuff down. Kenny's having a party. When your osteoclasts break stuff down, what happens is they actually they go through this process called apoptosis, where they will self-destruct afterwards, which sounds it's kind of sad. But they're like, my journey is done. I've eaten all the calcium I need, and then they go and they blow up, and then all that calcium is released sort of into the area, and then when the osteoblasts, the bone builder uppers, come along and lay down this glue, it attracts all that calcium back down. And that's how your bones are not just like, you're not just breaking down calcium and building it up, you're recycling your calcium over and over and over again. And so, you know, we want to have those things working together in conjunction with each other. So any questions on bones before we move on to the next part of our skeletal system, the joints? Questions, comments, concerns, guys? You feeling good? Yeah, what's up?
Yeah, pretty good.
Oh yeah, I was just he said something about something happens to the bones like age 25 or something. I'm not, I didn't understand or hear it too well.
Yeah, so it depends on who you are. Women are going to do this a little bit earlier than men. But yeah, generally we continue growing until we're about 25. So your bones are remodeling. This is why, it's sometimes a good idea to get certain, like if you're going to, have like a serious surgery or something, it's sometimes a good idea to get it done when you're younger, because then like your body will actually come back from that injury a lot faster than when you're a little bit older, because your body is still in growth mode. But yeah, after about 25, we're pretty much fully matured. So we're not like necessarily like growing any as much, new bone tissue. So that's another reason why, and we're going to talk about this in this module, because this is the youth mod, right? We're going to have our youth program design class. It's very important to like make youths exercise and get them engaged in physical activity at a young age, because that can trigger greater athleticism when they're an adult. It sets them up for like a good, strong foundation into adulthood. But yeah, you're basically matured by about age 25, Kenny, especially, as like a guy. Erica, she's the only lady in the room, a little bit earlier, usually 23, 24. That's why you hear like women mature a little bit faster than men do. All right, so let's move on to joints. Okay, so joints, this is what we're describing. We're talking about, it's the fancy name for a joint is going to be an articulation. It's where one bone is articulating with another, right? Where they sit into each other. And it's where they can, be manipulated and move around. So there's three main types of joints. The ones that we're going to spend most of our time talking about are synovial joints. Those are probably the ones that you're most familiar with. But there are three different types. There are fibrous joints. Fibrous joints are basically totally immovable joints. These are, they are like two bones coming together, but like they are not designed to move at all, right? So a good example of like a fibrous joint is like, the sutures between your skull. We think of our skull as like one big circular bone, but it's not. It's actually a bunch of plates all coming together, and they're all kind of threaded together like this. They don't have any joint cavity, because we don't want them to move at all, right? So those are completely non-movable joints. Then we've got cartilaginous joints. These are semi-movable joints. They also don't really have like a joint cavity. They don't have like a lot of space between them, but there is just a little bit of cartilage between them, right? And so these are your semi-movable joints. A really good example of this is like your pubic symphysis, which if we look at that, pelvic. If you look at your pelvis bone right here, where these two bones come together, right? That's a semi-movable joint, right? That's designed to just do like a little bit of rotary movement, maybe a little bit of elevation, depression, a little bit of forward to backward movement, right? Just ever so slight, but it's really not designed to move, the way like all of our joints are designed to move. And even your vertebrae, there's a lot of like cartilaginous joints in between those as well. Again, semi-movable, not fully movable. But then we've got the joints that you're probably most familiar with, which are your synovial joints. And synovial joints, what makes them special is that they have a really big joint cavity, which means that there's a lot of space in between. And what's great about having all that space is that means greater movement, right? The more space there is, the more movement there can be. So they have a big joint cavity, and they have synovial fluid in that joint cavity, which sort of acts like grease on a hinge. It's there to make sure that there's not too much friction in between the bones, So we go back to like this version here, you got both types of joints here. You can see this is a cartilaginous joint. It's really not designed to move that much. And then here, this is a ball and socket joint, which is a type of synovial joint. So this is a synovial joint here that can do all kinds of it. This is the second most mobile joint in your body, right behind your shoulder blade. So, a lot of space here. And this is also one of the reasons why, one of the things that we tend to see is as like a difference between like men and women. Women have a little bit more space in between their joints. And so because they have this slightly larger gap in their joints, it's why we tend to see women be a little bit more flexible in certain areas compared with men. That little bit of extra space translates to a little bit extra mobility. So we want to have space between our joints because that allows us to move. So those are your synovial joints. Like I said, they're fully movable, and there are special structures that are going to be found in your synovial joints. And these are the special structures we're talking about earlier. Your skeletal system, not just your bones, right? It's your joints and your connective tissue. So that connective tissue that we're going to talk about, primarily we're going to talk about ligaments, cartilage, and synovial fluid. Now there's a few other ones out there, right? There's sometimes you'll have like a meniscus or something, but these are the three primary ones that we're going to see in most of our joints. So you can see here this sort of like white webbing that is like covering here. These are your ligaments, right? So let's take a look. You can see like this is the ligament. That is holding your femur onto your pelvis, right? And there's tons of it, right? Like look at how much, connection there is. And that makes a lot of sense because this is the largest bone in your body. It's attached, your gluteus maximus is attached right here. That's the largest muscle in your body. There's a lot of force that goes on through the hip. So we want to have a really good, strong cord that kind of holds all of this together, right? Look at your knee here. These are some of the other strongest ligaments you've got in your body, right? You can see, actually you can't see any ligaments in this picture, but you can see these other materials, right? You see there's some cartilage here, right? Surrounding the bones, preventing friction. There's also, you're gonna see like there's a meniscus here and a meniscus here. Actually, that's not a very good, basically you're looking at one meniscus here and then the other one will be on the back side of this picture. But your meniscus are basically these little pieces of cartilage. They sit kind of like this, that creates like a big deep cave, and that way like your femur can't slide off of the top of your tibia. And then on the inside you're going to have your ACL ligament, which we always hear about when we're watching football and stuff, right? You're going to see your PCL ligament, you're going to see your LCL and your MCL. So there's ligaments like crazy in the knee because it's a very, very mobile joint. This is actually the largest joint in your body just in terms of sheer size. So we got a lot of ligaments to hold all those structures together. And then you can see here, there's a fat pad down here that's actually meant to prevent a little bit of friction with your quadricep tendon here. And then see these little things right here, these little like circles. Those are your bursa. And bursa are these little fluid-filled sacs that are also there to prevent friction. So all this like hard bone-on-bone tissue, we're trying to prevent as much friction as possible inside of our skeletal system. And so we've got all these structures, we got ligaments holding them together, we got cartilage to reduce friction, we got synovial fluid to reduce friction, and we've got sometimes fat pads and bursa and things like that as well. So here's what you need to remember. We're going to talk about ligaments, and then when we get to the muscular system in a little bit, we are also going to talk about tendons. One of the biggest struggles that like a lot of new students struggle with is getting the two of them separated, because what sucks about the world of anatomy and physiology, actually, let's look at knee joint. What sucks about studying anatomy and physiology is that anatomists are constantly drawing ligaments and tendons in the same way. So you can see here, right? See this muscle? It's red and bloody and like most of our muscle is going to be, right? But then it turns sort of this whitish color here before it inserts onto the bone down here on our tibia. That's your quadriceps tendon, and it's a tendon because it is attaching our muscle here to our bone tissue. But then we see over here this ligament that's attaching the femur to our fibula, and there's another one attaching our femur to our tibia, right? These are ligaments, and they look really similar when we draw them, but they could not be more different. Well, I guess they could be more different, but they're very different. Tendons attach muscles to your bones. Ligaments attach bones to bones. So tendons is a muscle conversation. Ligaments is a bone conversation, right? So that's what we're seeing here, right? We're seeing ligaments are soft tissue that attach bones to other bones. Cartilage is soft tissue that prevents friction. And synovial fluid is this gooey, viscous material that kind of looks like egg whites, actually, in between your synovial joints that is there to also prevent friction. Now, talking about how our, some of the interesting shapes in our joints. Now, this is not going to be a huge thing. I put these in the notes because I wanted to mention them now, just so that they're in the back of your brains. But we are not going to quiz you guys too much on types of joints or joint movements in this course. because we don't have kinesiology in this module. But next module, when we get into kinesiology, talking about the different types of joints is actually a big part of our conversation here. Put that chat bubble, open up. Why is my chat window not opening? Hold on a second. I know Woody's saying something. Come here. Really? Is it down? Is it just behind everything? It is. Really. There we go. Yes. So yeah. Cody, do you mind if I share that with everybody?
Yeah, sure.
Yeah, we were talking about this, right? So you had surgery on your ankle, because let's look at the ankle joint here, right? And if we look at this, and actually, I wish I could get, actually, that's a pretty good picture here. All right, so here's a really basic image of our ankle joint, right? And you can see all these different ligaments that are here attaching these bones to each other, right? So you can see here's your fibula, and it's attaching with what's called your calcaneofibular ligament. And then there's this one right here, which is arguably the really important one. This is your ATL ligament, right? Different from the ACL ligament, but it's your anterior talofibular ligament. Yeah, and so this is actually attaching, the fibula, which is this outside bone here, to the talus. I'm sorry, the calcaneus, which is this which is the front of your big heel bone here. And so this whole thing's attached here. And then there's another ligament here. There's all these ligaments in your ankle, right? Look at how much connective structure there is in your ankle. It's a very, 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 very complicated joint with a lot of moving parts. This is why ankle sprains are the #1 most common injury in all of athletics. There's just a lot of stuff that can be damaged here. And then the other thing that happened as well, so because you deattached that, there was nothing basically holding it in place to the side here. So what started happening is your fibula started sliding down your leg here, which luckily, from what you told me, it didn't really do too much to your knee, but it could also mess up the outside of your knee sometimes. But this bone here started sliding down because it was no longer attached. And then the space between these two bones, if we look at like your tibiofibular joint, if you look at this, there's two tibulofibular joints. There is the superior fibular and the inferior one, right? So they got two joints between these two bones here. And look at all this fascia that's there to hold the bones together. All that fascia got stretched out and damaged, and your body tried its best to repair it and created like a lot of scar tissue and stuff. So that damage in the ankle there is pretty severe. And unfortunately, like if it's a grade 3 tear, I mean, when you look at like these ligaments here, if you get like a grade 3 tear where you tear all the way through it, your body can't repair that, like the ligament is deattached. It's not like, you got to remember, like, if we deattach something, we just grab our hands and pull it back together and duct tape it, like your body can't do that. These are things that kind of moved apart. And so cells, immune cells might have headed to the end of that ligament, and then they're like, I can't reach across that gap, so when you get really severe, either muscle tears or really, really severe fibular tears, you got to get in there and have them like fully repaired. But that's essentially what happened. This is the soft tissue that was attached to hard tissue. So, if you get hit really hard, because you said this happened during football, right? You get hit really hard, or you make a really hard, wrong step in the wrong direction, or somebody twists really, really hard. You've got this really hard tissue that's being attached by soft tissue, and the hard tissue moves and it rips the soft tissue. And so we got to repair that. That's a lot of what we spend our time doing as personal trainers is, helping our clients get their mobility back by, improving the extensibility of that soft tissue. And then if it's nice and like flexible, what's great about that is like next time somebody maybe rolls their ankle, the ligament gets stretched out, but it's able to handle it, right? Because it's been used to getting stretched. It's nice and pliable, rather than being really stiff, which is what we see in most of our clients.
Yeah, it's just weird though. An ankle sprain that I did a sharp cut on, and all of a sudden I tore my ligament completely off.
Yeah, I mean, that's the thing. Your muscles were developed greater than your ligaments were, and that's a very common thing. For those of you who, I mean, almost everybody on this call, you guys have been through your first program design classes, right? So one of the things that we talk about in program design is the development of stabilization, right? We develop, these high repetition schemes in very unstable environments, right? And what that does is that, because of the high reps, it gives blood flow more time to get to the soft tissue. And because we do it in an unstable environment, you recruit that soft tissue more and more and more. And that's the thing, man. When you watch, that's the difference between, and I've said this before, I hate high school football. I really, really don't like high school football. Mostly because some of it's like the mentality behind high school football. I think the atmosphere is not exactly healthy in the way that we train athletics. And don't get me wrong, there's benefits there, that it teaches companionship, camaraderie, and work ethic and stuff. But sometimes that mentality of rub some dirt in it and get back on the field, right? That honestly is fine if you're a pro NFL player who has access to thousands of dollars worth of training and this and that and repair. But on a high school level, we constantly you've got high school football coaches who might know a lot about the sport of football, but know very little about how to train an athletic body in a way that will keep it from getting injured, just like our clients who often, I mean, probably a lot of people in this call right now, before you came to this school, your first intro into exercise was either looking up YouTube videos or maybe reading a magazine or watching somebody else in the gym and just or maybe sitting down on the machine and looking at the pictures on how to do it, right? That stuff's really great at developing strength in big prime movers like your pectorals and glutes and hamstrings and stuff, but it's not so good at getting all the little micro muscles that hold your joints in place. So, you've got a situation where, yeah, you made a big, strong cut because you got big, strong muscles that can recruit for a lot of force. But then you've got all those little tiny micro muscles that just weren't able to keep up, and that's where we see a lot of damage like this. If we'd spent more time during the development of your training focusing on stabilization and stuff, your likelihood for injury would have bottomed out through the floor. You would have been much less likely to get hurt. But and then that's a longer conversation, but I just got on my soapbox. I very much don't like a lot of high school athletics in the way that they are taught. Football is the best example. It happens in all the sports though. It's just that coaches get trained really well on how to lead a team to a sport, and they don't get trained very well on how to develop a body to handle that sport. And they get away with it because kids, for the most part, are very bendy. And for the most part, youths are really pliable. They're almost injury proof. They're made of freaking Laffy Taffy. But that only goes so far. All right, stepping off the soapbox. Let's move on to our types of joints here. So, types of joints that we've got. Okay, so we have got primarily what are going to be called gliding joints. And again, you guys don't have to have these memorized, but I want to go through them so that they kind of feel familiar when we get to them in kinesiology. Gliding joints is going to be where two bones are going to glide along the surface of another one. So your joints in your wrist and your ankle are a really good example of this. When I pulled up that picture of the ankle joint, your bone, you've got about, I think 26 bones in your foot, depending on who you ask. And so you'll see they're all what are called cuboid shaped bones, the little square bones. And so these cuboid bones of your ankle, they've got to be able to slide across the surface of one to another, right? So they do this sliding action there. Here's a random fun fact for you from my past. When I was a kid, my parents got me a Batman costume because I was obsessed with the Michael Keaton Batman movie. I used to watch it literally every day. And so I dressed up like Batman and I went over to a friend's house. I was 5 and I climbed up a tree and jumped out of that tree. And you know, I can't fly, but then again, neither can Batman. So this was a dumb idea, even as a 5-year-old. If I'd worn a Superman costume, I would have been fine. But I jumped out of this tree and I shattered my ankle. I broke 22 of the bones in my foot and ankle when I was a little kid. But luckily I was 5. And when you're 5, your osteoblasts, the bone builder uppers, are super, super active. So I was able to come back from that injury with pretty much no long-term repercussions, but completely basically liquidized my ankle when I was a little kid. So those are your gliding joints. It's, you know, your wrist is a good example of that, right? These little tiny itty bitty cuboid bones here, they're gonna glide kind of like this. Then you got hinge joints. Hinge joints are, they primarily allow movement in one direction only. So your elbow is a really good example of this, right? Now, obviously you're like, well, wait a minute, you can do this, right? I can twist my elbow. Yeah, totally can, but that's actually a different joint. When I talk about the elbow joint, I am just talking about the joint between the upper arm here and the lower arm here, where it mainly meets. That is a hinge joint. If you look at that elbow joint here, you can see where your humerus, the upper arm bone, is meeting with your radius, right? That's your actual elbow. The twisting is happening between your ulna, which is the other forearm bone, and your humerus. So that twisting action is not actually technically part of your elbow. But that hinging action, right, going primarily back and forth in one direction, that's a hinge joint there. We've got pivot joints, which are kind of fun. This is allowing like rotational movements. Like your vertebrae are a really good example of this, right? Being able to kind of rotate like this, right? So we've got hinging again, we've got gliding, and now we've got pivoting, right? So like twisting actions, even just like a little bit. These are not officially pivot joints, even though they can do a little bit of twisting. But like full twisting action, right? That is your pivot joints. You've got condyloid joints. This allows like a movement in 2 different directions. So when we think about like condyloid joints, we're looking at like your metacarpals here. So when I say your metacarpals, I'm actually talking about the palm of your hand, okay? So your palm primarily moves in 2 directions, right? There's a little bit of action going this way, and there's a little bit of action that goes this way. So they can kind of do this and this, right? That's a really good example there. So, you know, your carpals, your wrist bones, they're gliding joints, but your metacarpals are condyloid joints. They do a little bit of hinging, and they also do a little bit of twisting there. And then we've got 1 saddle joint in our, well, you got 2 because you got 1 on each side. But we do also have our saddle joints, which is very similar to a condyloid joint, except it's got this little bit of extra movement, and that's your thumb. This is a super important part of human evolution, actually, having this really specialized joint here that has allowed us to freaking use tools and be just a very, very accurate in things. Let me tell you, man, the thumb is about as cool as it gets. And that is a saddle joint. And so it is able to do all the things that your other palm muscles are able to do, where it kind of goes like this, but it is also able to kind of do this little extra motion. But that's also why it's not a ball and socket joint. So it's not as mobile as a ball and socket joint, which is why when you're trying to do like a rotation with your thumb, you'll feel it kind of snap from one side to the other. But that's the saddle joint because it kind of looks like a saddle of on a horse. And lastly, we've got the ball and socket joint. The ball and socket joint is the joint that allows the greatest amount of movement. It can do every single joint action simultaneously. So your hips and your shoulders are the 2 ball and socket joints. That is the most mobile joint inside of the body, which is great because, you know, lots of movement. Holy crap, we're happy for that. But the downside to that lots of movement is that we also have a lot of shoulder dislocations and things like that, because it is also a very large joint held only together, again, with ligaments. So if you've got a lot of movement, but not a lot of stability, you can dislocate your shoulder. Really quickly, we are also going to talk about our movements. These are some of the most important terms. You'll remember we talked about our directional terms and anatomic locations. Movements of your joints is another huge part of the conversation when we are talking about, you know, how to train our clients. Again, we are going to go over this way more in depth when we get to kinesiology. But talking about our movements, we've got different examples here. We have got what is called flexion and extension, and these all have their opposites, right? Whenever you have one movement, you are always going to have an anti-movement. So flexion is going to be a decrease in the angle between two joints, and it has to happen in the sagittal plane. So a perfect example of that is looking at like my elbow, right? So if we look like this and I bring my elbow from here to here, that is elbow flexion. And the reason why is because right now this joint is at if you were to use a protractor and measure the angle, this is 180 degrees. Now it's at 90 degrees. Now it's at 45 degrees, about 30 degrees overall when it gets to the end, right? So that is elbow flexion because the angle is going from 180 up to about 30, right? The angle, the number went down. That's a decrease in the angle, right? So that is flexion. The exact opposite of that is 30, 45, 90, 180. That's extension. So this is elbow flexion. This is elbow extension. Same thing is true in my shoulder. That is shoulder flexion. This is shoulder extension. So it has to happen in the sagittal plane of movement. You'll remember the sagittal plane from day one of class, right? So sagittal plane movements are front to back movements. So they're happening in this direction. So again, shoulder flexion, shoulder extension, spinal flexion, spinal extension, right? Neck flexion, neck extension. Now, you've also got in the frontal plane, we've got abduction and adduction. Abduction is this type of movement where my arms are being abducted by aliens, right? So my arms are being abducted away from me, right? So this is a frontal plane movement, right? The side to side type movements. So if I am moving away from my midline, right? So my midline is here. If I'm going away from it, that is abduction. If I'm going towards my midline, that is adduction, right? And those are two of our frontal plane movements. And then we have what is called circumduction, which is a rotational movement that happens everywhere. Actually, I'm going to get this. Why is circumduction next? Let's do rotation first. So there's also in the transverse plane, there's rotation. Rotation is a rotary movement, right? So this is neck rotation, right? This is right to left rotation. This is left to right rotation. But even just going like this, right? This is internal rotation. This would be external rotation, right? Because I'm coming from the anatomic position. I bring my thumbs in, right? That's internal. If I go from here and I go back out, that's external, right? So those are my rotational movements, internal or external. And that was transverse movement, right? And then there's circumduction, which is also a transverse movement, but this is every motion happening simultaneously. So circumduction is something like this. There's a little bit of abduction, a little bit of adduction. There's a little bit of flexion, a little bit of extension, and a little bit of rotation happening all simultaneously, right? So, you know, using like a lasso, that's a great example of circumduction. Then there's all the really special ones, which I didn't put in. These are kind of the main ones. These are kind of like the key players. These other versions are special versions that become part of a much more complicated version of the conversation. So I put these up here so you guys can see them and start getting familiar with them. Again, this becomes like very important lingo when we get to kinesiology. But there are some other ones. There's supination and pronation. When we talked about the ankle, when we talked about the forearm, we said, you know, how it can do this special little rotary movement here. Supination would be flipping your palm face up. Pronation would be flipping your palm face down. Same thing is true of your ankle. If you twist your ankle like this, right, and show it towards the bottom side, that's going to be known as eversion. And when you inversion. And when you twist it and show the bottom of your foot towards the outside, that's going to be called eversion. And if you do that with a little rotary movement at the same time, you have ankle supination and pronation. Again, it gets kind of complicated. We'll talk about that later. The ankle gets all these special terms. You've also got dorsiflexion and plantar flexion, which are basically like flexion / extension again. just happening in the ankle. But because like the angle is weird because your foot isn't, you know, going straight like up and down, it goes, you know, it goes, it's already, your ankle's already positioned at a right angle, like poking out of your body. It gets special terms. They're both technically a flexion version. So there's dorsiflexion, which is bringing your toes back towards your face, and plantar flexion, which is pointing your toes away from your face. So there's all the special versions. Don't worry too much about this for now, guys. You might see like one or two of these terms, but for the most part, this conversation becomes more important when we get to our kinesiology class. So again, we got flexion and extension. They're using the palm here. So yeah, flexion, extension. We've got pronation versus supination. Here's the way to remember that, by the way. Give me soup. Palm up, right? Abduction versus adduction, circumduction, left to, internal versus external rotation. Your ankle would be dorsiflexion or plantar flexion, or inversion or eversion. Whew, a lot of terms. We'll be looking at those way more in an actual kinesiology class. You know, I don't expect you guys to learn those in, 5 minutes? We lost somebody. Okay, so let's move on to the next part here. Let's look at the muscular system. Do you guys have any questions about those movements, or any questions about the joints and stuff? Are we feeling good about that? Who did I lose? Oh man, my brain. All right. Oh, it was Raul. Raul was in here. All right, let's take a look at our muscular system. All right, so this is gonna be chapter 8, and this is so fun. I love the muscular system so much. Just so many really cool moving parts here. So we've got 3 main types of muscle in our body. We've got smooth muscle found in your organs, cardiac muscle, which is just your heart all by itself, and skeletal muscle, which is the muscle that you're probably thinking of. That's your bodybuilding muscle, right? It's the muscle that moves your skeleton. We got a bunch of different systems here inside of it, and how, what their structures look like and how they're built. You got muscle layers, you got the junction where they meet, how they make energy, what exercise does to them, and then we'll look at the different types of contractions that we make as well. We've got the mechanics of how they attach and move around. You got your tendons and agonists versus antagonists, groups of muscles that we're gonna really not look too much at. The effects of aging on our muscular system, and then some of the disorders of our muscular system. So again, some key terms you might want to start to get familiar with. But take a look at our 3 types of muscles here, right? So, actually first, defining our muscular system, right? So your muscular system is a series of muscles and tendons and connective tissue that is responsible for producing movement throughout the body. So you've got your muscles here, right, which is really the main structure, made up of muscle fibers, which are your muscle cells. They get their own special little name because they look so unique. And then you've got your tendons, which attach your muscles to your bones. And then you've got little types of connective tissue. You get all this fascia running throughout your muscles. We kind of talked about that a little bit earlier. Now, looking at just muscles all by themselves, right? You've got 3 primary types here. You've got smooth muscle. Really good example is that of like the walls of your organs, right? Like your digestive system has to like squeeze food around so that it, travels throughout the whole system and eventually works its way out of the body, right? That is smooth muscle, right? Then we've got cardiac muscle. That's found in your heart. Cardiac muscle looks a little bit different. Like take a look here. Smooth muscle is very smooth. It doesn't need to make really strong contractions, Like I don't need to like do a 20-pound dumbbell curl with the parts of my small intestine. But I do need to be able to like get a little bit of food to travel from here to like here. And then the next part of my, got to keep it moving, right? So it doesn't have very many striations, which means it doesn't have very many fibers that are creating like big contractile, squeezes, right? But your cardiac muscle does. Your cardiac muscle has to be able to like squeeze to drive blood into and out of the heart itself. So it has a little bit like more striations in it because it's going to squeeze much harder than your smooth muscle is. But that is nothing compared to your skeletal muscle, which has these massive striations, right? Striations are where we can literally see when we're looking at muscle from like our regular vision, without a microscope even. You can see the little stripes on muscle fibers, right? Where, you know, it's grabbing and pulling, creating these contractions and relaxations and contractions and relaxations, right? That is your striations there. So skeletal muscle is responsible for manipulating your skeleton. When we look at skeletal muscle, its primary jobs are to, again, move our skeleton, also to maintain our posture, you know, keep our body in the alignment that it is best suited to generate and accept force. And it does generate heat. I mean, like, you know, one of the ways your body is able to like maintain plenty of heat is through like your muscles doing little contractions. It'll quiver when you get really, really cold. It also has like massive amounts of blood flow, and it generates a lot of energy. And so that energy releases heat into the body, keeping us at a temperature where our cells can function, and, you know, we can do maintain our, you know, our life, right? So let's look at the structure of a muscle here. Actually, not yet. Nope. I gotta show my video first. All right. So this is another one that gets a little bit complicated with some moving parts here. So I want to show you guys. So I want to show you a little video here that's going to break down the muscular system so that you can kind of understand what their shape and function really, really looks like. And who would have guessed, but it's another treadmill ad. Freaking Proform and Nautilus. And the other really big one, I don't remember its name. All right, here we go. Oh, by the way, pay no attention to this man's exercise form. He is here to teach you biology, not how to exercise, because he is not good at it. Love me some Hank Green, but this is not his forte.
Well, hello there. You caught me while I was working out. Last time I was lifting weights during a Crash Course episode. Also, the last time I was lifting weights, we were talking about how all of this is possible because of cellular respiration, the process our cells use to get and store energy from the food that we eat. Remember that? Good times. As it happens, a lot of what we learned then is also really helpful in understanding the organ system that we use to do our gun blasting and walking and fork and knife operating and parkour and playing Assassin's Creed and, you know, like moving around. I'm talking about your muscles, of course, and you wouldn't be able to move them without the help of that same molecule that your cells use to get all their jobs done. Good old adenosine triphosphate. Now, your muscles may be your body's most obvious moving parts, but as with all things that are truly worth learning about, this system is both way more complex and way more awesome than it first appears. Yeah, why? Because of chemistry. When you think of muscles, your mind usually goes straight to the guns there, but you really have three different types of muscle in your body. You have the cardiac muscle, your heart muscle, which is different from all the sorts of muscle in your body. And then you have smooth muscle, which is responsible for carrying out most of your involuntary processes, like pushing food through your digestive tract and pushing blood through your arteries, important stuff there. And then there's the muscles that you're most familiar with, the skeletal muscles. Your gluteus maximus, your masseter, which is, you know, important for chewing your hot pockets, the abductor pollicis brevis, right at the base of your thumb, aka your video game muscles. That's important for the Assassin's Creed. Just some of the 640 skeletal muscles you have. Those muscles, like all of your muscles, are only good at two things: contracting to become shorter and relaxing back out to their resting length. That's all muscles do. They contract and they relax. Pretty amazing that you can make a ballerina out of that. If you were to peel back my skin and take a look at one of my muscles, please don't do that, but if you did, you'd see that it thickens in the middle at what's called the muscle belly, and then it tapers off on either end into a tendon. Tendons are made of fibrous proteins, mostly collagen, that connect the muscle to the bone. Just a side note, ligaments, similar to tendons, but instead they connect bones to other bones. These muscle tendon combos stretch across one or more joints. In this case, it stretches across my elbow, so that one bone can move in relation to the other bone. So I just moved my arm, and now I'm moving my mouth, and I'm basically moving my whole body right now. And the question is, how am I doing this? How am I moving all of these things in all this sort of amazing fluid ways? How am I able to do that at all? Unfortunately, It's kind of complicated, but it's wonderful and amazing, so it would be worth it in the end. First, we need to understand the anatomy of a skeletal muscle, which includes many, many layers of long, thin strands. Think of one of your skeletal muscles as a rope. It's made of smaller ropes that are bundled together, and then those ropes are made of bundles of thread, and those threads are made of tiny, tiny filaments. This structure is what makes meat stringy, because after all, meat is just muscle. This chicken breast is, or was, the pectoralis major muscle of a chicken. It connected the bird's sternum or breastbone to the humerus in its wing, and sometimes I feel like chickens have bigger pecs than I do. It's crazy. When you peel this muscle apart, you see that it's really made up of layers of thin strings. These are muscle fascicles, and each fascicle is made up of lots and lots of smaller strands. These we can't see. They're called muscle fibers, and these are the actual muscle cells. Now, because muscle cells perform such a specialized job, they're not like your run-of-the-mill somatic cells. For starters, they each have multiple nuclei. That's because each muscle cell is actually formed by a bunch of cells, somewhat like stem cells called progenitor cells, fusing together. Muscle cells are basically just bundles of complex protein strands, and since nuclei are essential for the protein-making process, muscle cells need lots of nuclei to make all the protein they need. From here on, you'll notice, by the way, that a lot of the stuff I'm talking about starts with the prefix myo or sarco, from the Greek words for muscle or flesh, respectively. Whenever you see those terms in biology, you know you're probably in muscle country. For instance, those protein strands that I just mentioned that make up a muscle cell are called myofibrils, and each one is divided lengthwise into segments called sarcomeres. This is where the action happens, my friends, because it's the sarcomere that will actually do the contracting and relaxing to create the muscle movement. Each muscle cell has tens of thousands of these guys, and they all contract together to make you do stuff. And this contracting and relaxing occurs through this really cool and complex interaction between two different kinds of protein strands called myofilaments. One myofilament is the protein actin, which are skinny strands that attach to either one of the two ends of the sarcomere, and the other is myosin, which is thicker and studded with these little golf club-shaped knobs along it called heads. Inside a sarcomere, these proteins occur in layers with a thick strand of myosin floating between several strands of actin. Just how many strands of actin depends on the muscle we're talking about. In this case, let's just say that there are 4, 2 sitting on top and 2 sitting on the bottom. Now, when the muscle cell is at rest, none of these strands are touching each other, but they really desperately want to. They're like middle school students in a formal dance. The myosin in particular wants nothing more than to reach its little heads up and do some heavy petting with the actin. The chemical dance that allows this to happen is one of the sexiest things that goes on in your body other than, like, sex. And it's known as the sliding filament model of muscle contraction, which reminds me of an interesting story. I mentioned last week that we didn't really have even a passing understanding of the human skeleton until the 1500s, which seems kind of tardy to the party to me, but that's nothing compared with this. We didn't figure out how muscles worked until 1954. In 1954, 2 teams of researchers independently discovered that the sliding filament model is how muscles contract. And as luck would have it, 2 of the 4 scientists who made this discovery were named Huxley. We've already discussed Thomas Henry Huxley, the father of comparative anatomy and Darwin's bulldog. Well, his grandkids were all awesome at something too, like Aldous Huxley, who wrote the novel Brave New World, Julian Huxley, who was central to the development of modern evolutionary theory, and Andrew Fielding Huxley. Andrew Huxley was a physiologist who, with colleague Rolf Niedergerk, set out to solve the muscle contracting mystery. Until the early 1950s, all we knew was that myofibrils were full of protein strands. At that time, most people thought that these strands simply changed shape and shortened, like how a spring recoils after it's been stretched out. And by the 1950s, we'd learned pretty much everything we could about muscle cells by using conventional microscopes. So Huxley and Niedergerk actually designed and built a new microscope, a tricked out kind of interference microscope which uses 2 separate beams of light. And with that, they found that during contraction, some protein strands kept their length the same, while others around them contracted. But at the very same time, British biophysicist Gene Hansen and Hugh Esmore Huxley, an American biologist who had no relation to the famous British Huxleys, were using another newfangled tool, the electron microscope. Using that, they observed that muscle fiber was composed of thick and thin filaments, the myosin and the actin, and that the filaments were arranged in such a way that they could slide across each other to shorten the sarcomere. So in 2 separate papers published the same day in the same journal, 2 teams proposed that muscle contractions were caused by the movement of one protein over another. I guess an idea whose time had come. Except it's not that simple. To understand how the sliding filament model works, the first thing to keep in mind is that in addition to needing a bunch of protein, muscle cells need to make lots of ATP. ATP, you remember, creates the energy for almost everything your body does. Yes, that goes for muscle movement as well. Another thing to remember is that some proteins can change shape when they come into contact with certain ions. Like we've seen that with the sodium-potassium pumps, for instance. Those pumps are proteins that can accept sodium ions outside a cell, and then they change shape to release them inside a cell. And also, suddenly at the same time, they become able to accept potassium ions. These shape changers are how cells get a lot of the day-to-day job of living done. In a sarcomere, it's calcium ions that change the shape of some of the proteins so that the myosin can finally have its way and grope the actin strands all around it. Then it'll drag those actin strands toward each other, causing the sarcomere to contract. But when a muscle cell is at rest, there are a couple of things that keep this groping from happening. The first is a set of two proteins wrapped around the actin. They're called tropomyosin and troponin, and together they act as a kind of insulation. Let's just continue our middle school metaphor. They're the chaperones. They protect the actin from groping. At this point, each little head on the myosin strand has the wreckage of a spent ATP molecule stuck to it. That's ADP and a phosphate, and the energy from that broken ATP is already stored inside the head. So yeah, the myosin has a lot of pent-up frustration. Now, while the muscle cell is resting, it's preparing a stockpile of calcium ions that it will use as a trigger when it's go time. This is done by a specialized version of the smooth endoplasmic reticulum called the sarcoplasmic reticulum, or SR. It's wrapped around each sarcomere and it's studded with calcium pumps. These pumps are constantly burning up ATP to create a high concentration of calcium inside the SR. And of course, whenever you create a concentration gradient, you know it's going to get used. So now we're ready for a muscle contraction to start. But what starts it? Well, stimulus, of course, from a neuron. Muscles are activated by motor neurons, and each sarcomere has a motor neuron nearby. When a signal travels down the neuron to the neuron synapse with the muscle cell, it triggers a release of neurotransmitters, which in turn set off another action potential inside the muscle cell. That action potential continues along the muscle cell's membrane and then flows inside it along special folds in the membrane called T-tubules. When that signal reaches the SR inside the cell, bingo, the SR's channels open wide and let all those calcium ions diffuse down that concentration gradient. The calcium ions bind with one of the chaperones, the troponin, which causes the troponin to rotate around the actin and drag the tropomyosin out of the way, revealing all of those super hot binding sites on the actin. With our chaperones distracted, the myosin, it totally goes to town. It reaches all of those little tiny heads along its length to bind up with the actin, and the excitement of that long-awaited precious contact finally releases the energy that came from breaking that ATP molecule. This burst of energy causes the heads to suddenly bend toward the center of the sarcomere, pulling the actin strands together and shrinking the sarcomere. In millions of sarcomeres, in hundreds of thousands of muscle cells, this is what allows me to, lift my arms. You wouldn't think it would be so complicated. Now, in order for the contraction to stop, you're going to have to tear those two proteins apart, because each myosin head is really comfortable here, snuggling with its beloved actin. So it'll take another passing ATP molecule to attach to the head, which breaks off one of the phosphates to release its energy as soon as they touch. That energy breaks the myosin's bond with the actin and lowers the head, leaving it alone and frustrated once more. So it's weird that the energy from the ATP is actually used to make the muscle relax. But in fact, that's why we get rigor mortis. When you're dead, there's no more ATP to make the muscle relax, and all the calcium ions diffuse out of the sarcoplasmic reticulum, causing the muscles to enter their resting state, which is contracted. But you're not dead yet, so let's wrap this up. When the myosin and actin are being separated, the sarcoplasmic reticulum is hard at work pumping all of the calcium ions back inside it and storing them up for next time. That lets our chaperones come back. The troponin and the tropomyosin retake their positions around the actin strand, resets the sarcomere for the next impulse to come along. Chemistry makes it all possible, from blasting your guns to my awesome dance moves. Thank you for watching this episode of Crash Course Biology. If you want to go back and look at some stuff, because it was a confusing episode today, table of contents. And thanks to everyone who helped put this together. This one was a doozy, so thanks to our head writer, Blake DiPestino. And of course, Amber, as always, for doing our amazing graphics. If you have any questions, please leave them down below in the comments or get in touch with us on Facebook or Twitter. We'll endeavor to answer you, as will all of those extraordinarily helpful people who are not affiliated with us at all, but are quite smart and helpful. So thank you to them, and we'll see you next time.
Okay, so let's say, let's go through that, but more slowly and more detailed. All right. So a lot of moving parts in the conversation about muscles, right? Now, obviously, we again, going back to our levels of organization, right? We know that any tissue is made up of cells, right? And so when we look at like a muscle's structure, we got to start the conversation by talking about muscle fibers. A muscle fiber is nothing more than a fancy way of saying muscle cell. We just call it a muscle fiber because like it has a lot of specialized parts in it that make it slightly unique. So rather than just referring to it as a muscle cell, we call it a muscle fiber, right? Now, that muscle fiber is going to be bound up with a whole bunch of other muscle fibers in a bundle that we call a fascicle, okay? And a fascicle is a bundle of muscle fibers, and then your muscles themselves are made up of a whole bunch of more bundles that make up the actual individual muscle. So if we look at like, muscle, actually, no, I want to look up a fascicle. So when we look at like a fascicle, you can see it's actually going to look like this. Oh, shoot, there we go. So you can see this, actually, that's not quite what I want. Sorry. I like this picture. I just don't like the fact that it has like a black background. Let's see here. Open up in a new, oh, it's got a gray background. Perfect. Okay. So this right here is an individual muscle cell, right? This whole thing right here, this is what your muscle cell looks like. And inside of every muscle cell, you can see there's mitochondria and all the normal materials. You're going to find nucleuses in here. You're going to find all the normal materials inside of a muscle fiber that you would find in any other cell. But it's got some other specialized materials, the most important of which is right here. This is called a myofibril, okay, or a myofibril. And that is where you are going to find little overlapping layers of these specialized proteins called actin and myosin. And what happens is the myofibril shortens like this. So there are all these myofibrils in a muscle cell. So when all those myofibrils shorten, the muscle cell shortens. Now, this muscle cell is bound together to this one and this one and this one and this one. They're all wrapped together in this big bundle. This is a fascicle, okay? It is a bundle of individual muscle cells. And muscle cells are a big bundle of myofibrils. Then that fascicle is bundled together with a whole bunch of other fascicles. So here's a fascicle, here's a fascicle, here's a fascicle, and all that's wrapped together. That's your actual muscle. So muscles are bundles of bundles of bundles. And then that whole thing is wrapped in an outer, sort of wrapper that we call your fascia, right? So a fascicle is a bundle of muscle cells that make up the muscle as a whole, and the muscle is an individual organ that is a bundle of muscle fascicles, right? So you've got a muscle fiber, then you got a fascicle, which is a bunch of muscle fibers, then you got a muscle, which is a bunch of fascicles, okay? How are we doing so far? Any questions? Am I moving too quick for anybody? Tell me to slow down if I go too fast. Don't let me get ahead. All right. So there's a bunch of layers that, if those are all bundled together, right, then there's going to be a bunch of layers that are holding them together. There's what is called the endomysium. That's the innermost layer, right? That's the innermost wrapper. That's holding together the wall of each of your individual muscle cells. So when we look at a muscle cell, right, it's got its little outer layer here that's wrapping all the myofibrils and nucleuses and mitochondria and stuff, right? It's wrapping all of it together. That has like an outer plasma membrane similar to any other animal cell. We just call it the endomysium, okay? Then you've got the paramecium, which is the outermost layer of a fascicle, right? So then, that is going to be bound together with all the other muscle fibers, okay? And there's a wrapper around the fascicle, and that wrapper is going to be what we look at when we see your paramecium. And then there's the outer uppermost layer that's binding all of those together, and that is your epimysium. And that's your fascia that's basically surrounding the outside of every individual muscle. And then there's going to be even some more fascia that's another layer outside of that. Then what's going to happen is that muscle is going to get really stiff and it's going to become less and less and less contractile until eventually it becomes a tendon. And then a tendon is going to attach to a bone. Okay, so that's where like the muscle gets really, really stiff. You've tasted tendons before if you've ever been eating meat and you get that part where it's like really stringy and chewy and you're like, ah, God, right? Like that's the tendon, right? It's the stiff stuff at the very, very end. Now, here you can see a kind of a picture of all this, by the way. There's an individual muscle cell wrapped together in a fascicle, and then all those fascicles wrap together to make up the overall belly of the muscle. And then that comes down and becomes like a tendon before it inserts onto a bone. And then now that's able to kind of pull on that bone. And here you can see that is your biceps muscle and your biceps tendon. Now, looking at how muscular contractions take place, and this is where it gets a little bit, this is where the really technical stuff comes in, right? But this is the stuff that you do need to know in order to understand how muscle contractions work. And they love to test you on this on the science chapters of your NASM test. So we got to understand how your nervous system is interacting with your muscular system. It is doing that through what is called motor units, okay? This is where your muscular system and your nervous system work very intimately together. So what a motor unit is, and I don't want to say this is the most important term of the day, but I'd say this is a really big one to remember. What a motor unit is it's a single motor neuron, okay? So that's the type of neuron that causes contractions. It's the type of neurons that interacts with your muscular system. So it's a motor neuron from the nervous system and all of the muscle fibers that it stimulates. So when you look at a motor unit, you're going to see it's going to be this big neuron that runs down, and then it's going to have like a finger here and a finger here and a finger there and a finger there. And then it's going to have, let's say 4, right? In this case, this single neuron is going to zap these 4 individual muscle cells, okay? These individual muscle fibers. Now you've got really big motor units and you've got really small motor units. You know, you might only use a couple hundred to move your eyes around, but you're going to use thousands to move your glutes. All under the control of like individual like neurons. So when you create new muscle fibers or larger muscle fibers, you create larger motor units. And that's how we develop our strength. You get a neuron which grows more fingers to basically zap more muscle fibers, right? So there's a motor, there's one neuron, there's another neuron, and there's another neuron. And maybe this one's only contracting with this individual little tiny muscle fiber, but these guys are controlling lots of muscle fibers. So this might be a really weak contraction, and this is a really strong contraction down here. So you do have small motor units for really fine little tiny movements, and you got large motor units for your broad movements, such as like squatting or bench pressing or deadlifting or, rowing or whatever. Now, the space where these are meeting, right, there's like a little area where your, obviously the neuron is interacting with the muscle fibers. That space is going to be what we call the neuromuscular junction. Okay, and this is where there's a little gap at the end of the finger of the neuron, right? You can see this is the end of the neuron, and then here's the individual muscle cell. And there's a little gap between those two, right? And so your neuromuscular junction is the point at which a nerve fiber interacts with a muscle fiber. It's where your nervous system meets your muscular system. And what we see there is, yesterday we were talking about exocytosis, right? We talked about how cells basically can sort of poop stuff out, right? That's really what it is. And so what happens at the neuromuscular junction is the end of this neuron creates it creates these little vesicles, right? These little pockets, and then that kind of moves to the end, and then it opens up the edge of the pocket to release this neurotransmitter. This neurotransmitter, by the way, is going to be called acetylcholine. Okay, and so acetylcholine is going to diffuse across the gap. It's going to move from this area where there's obviously a lot of acetylcholine, and remember, nature hates having a lot of stuff in one place, so it's going to move away to the other side, and it's going to bind to the muscle cell. And when that happens, there are receptors on the muscle cell, and when that acetylcholine binds with it, it triggers the muscular contraction. So that is how your nervous system tells your muscular system to do its job, right? So you're going to have the motor neuron, at the neuromuscular junction, the place where these are meeting, you're going to have the motor neuron itself. You're going to have the motor end plate, which is on the muscle fiber, and you're going to have the neurotransmitter acetylcholine, which is going to, trigger this reaction, right? So what's going to happen is it's going to stimulate that muscle fiber to generate electricity. The muscle fiber is basically going to run this big electric shock along the entire muscle fiber. And when that electric shock happens, it triggers the contraction inside of the muscle. Okay. That is happening in every muscle fiber simultaneously. And then that causes all the fibers to shorten, which causes the entire muscle to shorten as well, right? So when we go all the way back, right, this muscle fiber is going to contract, and so is this one, and this one, and this one, and this one, this one, right? All those fibers are going to contract, and then, that's going to cause the whole fascicle to shorten. Meanwhile, it's happening to all these other muscle fibers as well. And so then those fascicles shorten, and the entire muscle goes from being this long to being this long, and it drags your bone with it. And that's how we create those contractions, right? Feeling good so far, guys? Any questions on that? The neuromuscular junction's a little weird. Everybody feeling good? Everybody's real quiet. All right. So let's take a look inside of an individual muscle fiber, right? So I did mention you've got these little myofibrils here, right? These little areas, this myofibril, these little contractile proteins inside of each individual muscle cell. So when we look at a myofibril, or myofibril, let me take a look at it. You can see it looks something kind of like this, right? Here's, an overall muscle cell. Let me zoom in like crazy. You can see it's this overlapping layer of proteins, right? You can see there's this little purple protein here, and then there's these little green proteins here. And you can see it's like this area where they are, that's a little too zoomed in. That works, I guess. It's this area where they're crossing over each other, creating this kind of zigzag motion, right? So that area where they are crossing is called the sarcomere. This, by the way, is one of your most key terms that we see. Oh, shoot, hold on. I got to get through some of the pictures here in the PowerPoint. I got a little ahead. There's the motor neuron. There's the end plate where it's meeting. It's going to release through exocytosis the acetylcholine. It'll bind to the receptor, and boom, that will kick off the muscular contraction. So looking at a myofibril, right? Looking at what that is. It is this overall like huge section here, right? Well, huge in comparison to what we're going to be talking about as individual proteins, but it's made up of these overlapping layers, right? So here's a really big myofibril running from end to end of the muscle cell. And then when we look inside of that myofibril, there's these little tiny itty bitty proteins, okay? And the area where those proteins are crossing over each other, from like this line here to this line right here, we call that the sarcomere, okay? And this right here is a term, this is the functional unit of your muscular system. Your muscular system is able to do what it does because it has sarcomeres, okay? And sarcomeres are where these little tiny contractile proteins are able to grab each other and pull each other, right? So it is where contractions take place inside of a muscle fiber, okay? Now, what are those little contractile proteins? Well, we call those myofilaments, okay? They're these special little proteins. And what they are is there's the thin filament, which is called actin, and there's the thin filament, which is called myosin. So actin is this special little protein that has all these little tiny binding sites on it, okay? So think about how zoomed in we already are in this picture right here. Well, we got to zoom in even further, right? Let's take a look at actin and myosin. When we look at these little filaments, take a look here, guys. You can see they actually look something kind of like this. You can see there's this little thin filament right here, and then there's this thick filament right here. And see all these little heads? These little heads are going to reach up, and they're going to grab the actin strand. Honestly, picture these guys as like, high school kids at like a school dance, right? They want to get all up in each other's business. But because they want to, that's what's going to create this contraction. But we don't want them to always do that, right? We want to have a relaxation in our muscles. So what'll happen is you can see these little heads, they really want to reach up and they want to grab these little binding sites right here. All these little like circles, this little head wants to reach up and grab it like crazy. And so that's what actin and myosin are. So you've got the thick filament, which is the myosin. Those are the little heads. And the thin filament is the actin, which has all the binding sites. So the heads want to attach to the binding sites. But luckily, whenever we have like a relaxed muscle, we've got these little regulatory proteins, which are blocking the binding sites. Those are called troponin and tropomyosin. And they're there to keep that binding from happening when a muscle is supposed to be relaxed. So how do we actually start contractions? Well, again, go back to that neuromuscular junction, right? In the neuromuscular junction, when we release that acetylcholine into the area, where's my neuromuscular junction? I close it. When we release acetylcholine into the air, right, this is going to kick off our muscular contraction. What's really happening is this is kicking off the release of calcium into the muscle fiber. And when that calcium gets released, the regulatory proteins, troponin and tropomyosin, these little bands right here, these little green and orange bands, they move out of the way because they are attracted to calcium. So that drags them out of the way, and now the binding sites are exposed. And so myosin reaches up and grabs actin, and when it does that, it pulls it like this. And so what happens is these fibers that are on this side, they move this way, and the fibers that are on this side, they move that way. And so they slide across each other, okay? That sliding action is what we call the sliding filament model, and it looks exactly like this. I'm going to show you a little GIF here. Is that going to work? Animated GIF, please. There we go. So they slide across each other all simultaneously, right? They reach up, and that causes all of them to slide, and that causes your muscles short. This is also why, like, when your muscles bunch up, right? It's because they are sliding across each other. So that bunching action is what creates this, right? So when we see this, and we look at the sliding filament theory, right, the sliding filament model, right, in the sarcomere, actin and myosin are overlapping each other, but they are at rest until the regulatory proteins move out of the way. And that is where the sliding filament model happens. It describes how myosin binds to actin and drags itself, shortening the muscle. This is happening in every single muscle cell inside of your body simultaneously whenever you create these contractions, right? It uses up a bunch of stored energy to pull it towards its center. That's happening in this sarcomere, and that one, and that one, and that one, and that one, and that one. And so the whole muscle cell gets shorter simultaneously, okay? So you can kind of see that right here, right? You can see the thick filament with all the little heads on it, right, is going to reach up and grab the thin filament, which has all the binding sites, and it will drag it towards its center, and that creates contraction. And then when you relax your muscle, it's basically just going to, put that calcium back in place, which closes up the binding sites and allows the muscle to go back to full length, okay? So this is going to break this all down. Basically, calcium is released into the area that moves the regulatory proteins out of the way. Myosin reaches up and grabs the actin, right? Binding sites are blocked. Oh, binding sites are open, right? It grabs it and it pulls it. So in order, for every single muscular contraction you've ever made in your entire life, here is the order that happens. That acetylcholine, the neurotransmitter, is released and it binds to the muscle. That creates an action potential, which releases calcium into the area. Calcium moves the regulatory proteins out of the way. Myosin grabs the actin and uses all of its stored energy to pull it this way, and this way, and then the muscle shortens, and then new ATP is attached, which allows it to relax and drives all the calcium out of the area, and it's pumped back in to get ready for the next contraction. Pretty complicated stuff, right? But that is how every single muscular contraction that you've ever done actually happens. And I'll be honest, guys, NASM does like to ask you stuff about this stuff. So, this is why, for those of you who have heard me say all of this stuff before, we do go over this in all 4 modules. This comes up literally every mod because there are questions related to this in your NASM test. Any questions so far? Erica, how you feeling? You're so you're not 100% new, but checking in.
I'm good.
All right, fair enough. I know you've been through some of this before. I just want to make sure that, I'm a trainer. I'm used to warming people up, but instead you're getting burpees on day 1.
Yeah.
All right. So, talking a little bit about our energy sources here, just before we actually get back into the note stuff here. All these muscular contractions obviously take a lot of energy in the form of ATP. And so your body is able to store this energy and generate this energy either through glycolysis or aerobic energy production. That is going to take oxygen and glucose in order to do that. So because of that, your muscles are actually able to store oxygen and it's able to store glucose inside so that it can have that energy production happen in real time. And it'll store it in the form of myoglobin inside of your muscles, right? That's going to kind of be similar to hemoglobin, except that it's the muscle version of hemoglobin. So that's storing oxygen. And then glycogen, which is the storage form of carbohydrates inside of all of your muscles. So there's sort of some starchy carbs stored in your liver, but mainly also also stored within your muscles. So during strenuous energy, obviously we're breaking down things like creatine to create muscular contractions and generate ATP. Sometimes we're producing lactic acid to produce ATP, and sometimes we are generating like aerobic metabolism to generate ATP. Our body will do it in 3 different ways. So what's great about that is there's obviously a lot of extra energy. So we got that excess post-exercise oxygen consumption, also known as EPOC. It's my favorite thing to talk about, where when you do intense activity, your body has to kind of catch up afterwards and it continues burning extra energy. So after strenuous exercise, you take in extra oxygen in order to remove that lactic acid and get yourself ready for the next round of exercise. And that can sometimes last all the way up to 72 hours. So every time you exercise, yeah, you burned some calories while you were exercising, but you burned a lot of calories after you were exercising, which we love. And we know that exercise has all these really great effects on our body, right? It improves our balance, our flexibility. It makes your muscles larger. It gets you better at vasodilation, so it keeps your blood vessels healthy. It strengthens your heart. It can help you control your weight through energy burn. And then it also obviously strengthens your bones. So, but this PowerPoint is not so great at teaching you about like why working out is awesome. That is much better left to the training PowerPoints, which we'll get to on Tuesday, I want to say. I think. So now we do got to talk a little bit about our types of muscular contractions. You guys will remember this from our last module if you've been through that. So the types of muscular contractions, we got 3 types, right? We are either contracting a muscle to overcome a force, or we are contracting a muscle to relax a force, or we're contracting a muscle to like stabilize a force and hold it in one spot. So those are the 3 types of contractions, right? So for instance, like if I shorten my muscle here, right, it's going to bunch up. That's a concentric contraction. And if I lengthen my muscle, that's an eccentric contraction. But then if I were to just like hold it in place and like try to contract, but I'm not letting it move anywhere, that would be an isometric contraction, okay? So of the type that we've got, right, eccentric contractions occur when a muscle is lengthening. Basically, your muscle is generating less force than whatever resistive force it may be dealing with. If I'm holding 10 pounds in my arm and I generate 9 pounds of force, my arm is going to lower down to the ground, right? That's an eccentric contraction because my fibers are being pulled apart. They're being lengthened, right? This is associated with force reduction, right? If I catch something, right, that's eccentric. Concentric contractions occur when the muscle is shortening. If I throw something away from me, I would overcome that resistive force, right? And my muscles would shorten in order to be able to do that. That's concentric contractions. Your muscle is generating greater force than a resistance. I've got 10 pounds in my hand. I generate 11 pounds of force. I overcome that movement, you know? That's force production. And then we've got isometric contractions. Like I said, this is where it's equal, right? So if I've got 10 pounds and I hold it like right here, I just hold it here for however long, right? I'm not letting my body move. I'm generating exactly as much force as it's being applied. That is an isometric contraction. The muscle is generating equal force or it is stabilizing, right? Now, the last thing we're going to talk about here, and looking at your muscles, right? Here's just an overall picture here. You can see this is your biceps, right? Now, on the opposite side of this bicep, if you were to flip to the other side, and they're not drawing it here, but you would also have your triceps, okay? And here's one thing that you guys need to remember about muscles, okay? Muscles control your posture, but they are arranged in such a way muscles can only pull. That's the only thing muscles can do. They can pull and then they can relax back to their original length. Muscles cannot push against in the opposite length. Now I know you might be going, wait a minute, I'd literally have an exercise called the push-up. Yeah, but when you're doing a push-up, right, it's this motion right here. That's what we call horizontal adduction, by the way. When I go like this, right, my pectoral muscles are dragging this bone this way, right? And so this muscle is shortening like this, and that's causing that movement to occur there, right? That's a shortening action. Just like if I were to pull in the opposite direction this way, these muscles would be pulling, in order to create a shortening action. So I can't push, my muscles can only pull. So what has to happen is I have to have one muscle on one side of a joint and another muscle on the other side of the joint. And that way, when this one pulls, this one can relax. And when this one pulls, this one can relax. And it creates this constant movement, right? That arrangement is really, really important to understand, like vitally important to understand, because that is how we understand posture, right? If I look at someone's posture and I see that when they squat something like this, right? Take a look at my knees, guys. If I squat down and I squat like this, right? My knees are caving in. This is really bad for my knees, right? And it's really bad. It's bad for everything, right? So if I squat like this, I as a trainer have to understand like what's happening inside the body, right? So clearly they're experiencing what we, at hip adduction, right? So that means that the muscle that does hip adduction is pulling too hard. Now, if one muscle's pulling too hard and muscles can only pull, what do I need to do to fix it? I need to make the opposite muscle pull for more force than that one. I need to get that muscle that's causing, the muscle that's causing adduction is pulling too much. What do I need to do? I need to do abduction. I need to do the exact opposite. So understanding this is key. And that's why we have a term for each of these muscles as we're talking about how they move, right? So when we look at your muscles and we look at like what you have, your muscles are all paired up to have their opposite, right? So muscles control you by pulling. Your agonist is the muscle that we're referring to. It is the muscle that's responsible for whatever movement we're talking about. I was just talking about hip adduction. So my agonist is what's called my adductor group, okay? My agonist muscle, right? So here's one. The example here, the pectoralis major, that's my pec muscle. It's the prime mover that is mostly responsible during a push-up, right? When I perform horizontal abduction, which is this movement right here, right? The pushing action, which is horizontal adduction, the prime mover is my pectoralis major, okay? Think of it as the main character to whatever you're talking about. It's Batman, right? Like Batman's the main character of, Batman comics or Detective Comics, whatever you want to call it, right? Like Batman's the main character here, right? Now, obviously, because we have to be able to pull in the opposite direction, we have to have a direct opposite muscle for every muscle we have in our body. And that's where you have your antagonists, okay? Antagonists are muscles that move opposite of your prime movers for whatever particular movement. So if I have my pectoralis major creating this motion, my rhomboid muscles in the back, or my deltoid muscles, they're going to do the exact opposite, right? If this does horizontal adduction, my deltoid muscle in the back of my arm does horizontal abduction, okay? So the posterior deltoid is an antagonist during a push-up. It's doing the opposite when I do my push-up, right? It is relaxing when this muscle is contracting. And the exact opposite should be true the other direction, right? When my elbow contracts, when my bicep contracts, my tricep should relax. When my tricep contracts, my bicep should relax, right? And so, like, if you want to think about it, that's Joker, right? The Joker, right? Total opposite of Batman. Batman's going that way, Joker's going that way, right? They're total opposites to each other. Now, muscles need to also have like a helper muscle, right? Your muscles often will need to recruit multiple muscles simultaneously in order to get a job done. And that's where we have our synergist muscles. Synergist muscles assist your prime movers. They're similar to prime movers, but they're there to help, right? So my anterior deltoid, which is right here in the front, that also does a little bit of movement during my push-up, right? So I got my posterior deltoid, which is the opposite. I've got my pec, which is the main muscle, and I've got my anterior deltoid there to help, okay? Think of this as like Robin, right? Like Robin's there to be Batman's sidekick, right? He's helping out. So you got main character, that's the agonist, the opposite character, that's the antagonist, and the helper character, that's your synergist. Now, while all of this is happening, one thing that we're not seeing in this PowerPoint, but is very important to us, we also have stabilizer muscles. And stabilizer muscles are basically isometrically holding your joints at whatever angle they're supposed to be at during particular movements. So like your rotator cuff, which is all these little stabilizing muscles inside of your shoulder joint, they are there to protect the body and stabilize it during whatever particular movement. So my rotator cuff's going to help stabilize while I'm moving through a range of motion during my push-up. Think of this as like Alfred the butler in the Batman stories, right? He's there to like provide emotional support and tea and crumpets to Batman, right? So that is sort of what we're seeing. Our agonists are the main muscle, our antagonist is the opposite, synergists are there to help, and stabilizers are there to hold everything in place to make sure that nothing, you know, your spine doesn't fall apart while you're doing like a body weight squat. I believe that is actually, oh yeah. There are some names here at the end. I honestly, guys, I would probably just not, the last part of this PowerPoint, the last part of the chapter, it starts to break down how muscles are named, which really isn't something we are going to spend a lot of time on. So I would say that's kind of a waste of energy. I wouldn't spend too much time going through this, but you know, they name muscles based on their size, their shape, the direction they might be traveling, what their job is, or where they're located in the body. And here's a general list of, you know, some of the most common muscles in the body. I love how sassy both of these pictures are, by the way. And here's like the muscle groups. If you want to start getting a little bit familiar with these, you can, but I actually don't think this is a very good working list. Again, this is written from the perspective of being like a medical class, not so much like a how to exercise class. So most of these muscle lists, these pictures here are really helpful, but like for labeling purposes, but like understanding like what they do and stuff, we're going to teach this much, much better in later classes. So I honestly wouldn't spend too much time working on that. Pay attention to these terms here because that is the stuff that you're definitely going to want to get familiar with before we move into the classes where, you know, we are going to teach it. All right, guys, that is about all I got for you today. I know it's a little bit of a longer lesson today, but, you know, muscular system and skeletal system, two of the absolutely most important things that we have conversations about. How's everybody feeling? Do you guys have any questions?
I kind of remember most of the stuff from the class you gave with Grish,
right?
But it's still a lot to take in, though. You know?
Mod 3, right? I told you I want you to be sick of this stuff by the time you're out of here. That's great. That's great, man. And yeah, you know, it is a lot, but yeah, hopefully it's coming around. Kenny, Andres, this is your second round of this stuff. How you guys feeling?
This one was not that bad. It was pretty Not as difficult as yesterday.
Love that. Love that. Should be a little familiar, right? Seen some of it before. Well, all right, guys. That's about all I got for you. You guys are on to your weekend. Hope you guys get to do something fun this weekend. Enjoy the miniature out of town trips for those of you. And then I guess we'll see you guys on Monday.
All right, Brad. See you Monday. Thank you.
All right, Brad. See ya.
Bye bye.